So I'm working on a project that has multiple layers to it. One of the layers is about having real-time peer-to-peer audio. And so to understand that aspect of the project, I decided to build a smaller project that is focused on real-time audio. That is what I have here, and it's called Extended Ears. So Extended Ears is using WebRTC to send and receive audio. So this is hosted on dr-esk.com, and it's available right now. And so let me demonstrate how this works. So first step is to register. And when I register, this username, this ID, gets registered on the signaling server. The signaling server is the external help that WebRTC needs in order to kickstart the process. WebRTC by itself has no means of allowing peers to find each other. There needs to be an external help that helps the peers discover each other. And so in this case, that external help is going to be a very simple WebSocket server that I happen to have hosted at this URL. The other two instances here that I'm showing are running on my two phones. And all I'm doing is I'm just casting the screens here, and that's how I'm showing them on the computer here. PC is registered, so the next step is to add a connection from this phone. I'm going to use this phone to add a connection. So first I'm going to register this phone. I'm going to call it phone 1, and I'm going to register it. Then I'm going to add a connection. So this pops a widget that allows me to specify the target ID. In this case, it's going to be uppercase PC to match this one. I'm going to hit connect, and that triggers the audio transmission. This audio transmission has auto gain control off, echo cancellation off, noise suppression off. I'm trying to have unprocessed audio for the purposes of this demo. Also, I don't have this toggle turned on. This toggle is about immediately sending reciprocal audio as soon as the audio is received from the peer. So in this case, this would have meant that PC would send its own audio from its own microphone to phone 1. However, I turned it off just to keep things simple. In this case, only phone 1 is sending audio to PC and not the other way around. But the web app supports both modes. Phone 1 is sending audio to PC. Now let's hear it. I'm going to switch to the feed that is coming through here. Okay, this is phone 1 audio, and I can tap on it, and I can see from the meter that it's pretty loud. So that's working. Let's try phone 2. So I'm going to register my other phone. I'm going to say phone 2. And I'm going to register. And then I'm going to add this audio connection. The target is going to be PC. I'm going to connect. And now there's probably a perceivable echo because there's two microphones at the same time streaming audio. However, it's possible that one of the phones is a lot quieter than the other. So either way, the audio quality is very high, and I've tested it already, and I'm very happy with it. In fact, the audio quality can be tweaked even more. So I have it this way. I have it set up this way. So this is the configuration JSON that goes into this WebRTC API. That is, by the way, a feature in modern browsers. WebRTC is already built in modern browsers, so I don't need to import anything. I just directly interface with the WebRTC functionality in modern browsers. So this is what that API accepts as in one of the places. And I specified 48,000 for the sample rate and 16 for the sample size. And this produces pretty good audio. So I'm just using it as a normal microphone right now, and I think it's pretty good. Let me switch back to the normal one. One other important thing about this web app is that I'm logging everything here. And in order to make sense of this all, I decided to do this. I built a sequence diagram out of these logs. So I'm logging in a specific format, in a specific way, so that I can produce the sequence diagram. So this particular sequence diagram represents this demo. So PC registered first, then phone 1 registered, and then when phone 1 registered, PC received an announcement about it, and then phone 1 initiated the process of the audio transmission. So it seemed like an instance when I tapped on the connect button. However, behind that tapping on the connect button, a lot was happening. In fact, this many things needed to happen from here all the way down to here before the audio connection could be established. What I'm going to do next is I'm going to go through the code. I'm going to explain how I built it. I'm going to keep referring to this sequence diagram to better relate it all to the WebRTC process. Let's have a look at the signaling server code first. So what I'm trying to do here is rather simple. I want to receive messages from the clients, and then depending on the message, I either forward that message or broadcast that message. If I broadcast that message, everyone in the room will receive that message. Another thing I want to do here is track the connection. So every connection, every client that connects to the signaling server will establish a connection, a channel. That channel is going to be represented by an object. So this is one example of that. I need to keep track of those objects because I want to maintain the awareness of where each client lives, which room each client lives in. So that's another job of the signaling server, is to keep track of the connections. And I do that by saving the connections inside the rooms object here. So I created an object called rooms, and I will preserve them there. In terms of actually building it out, it's rather simple. I import the WebSocket here, WebSocket library, and then I use this library to create an instance of the server. And then after that, I'm ready to listen to connections. So let's have a look at this. So when a connection event occurs, meaning when the client connects to the server, this callback function will execute. This callback function takes this parameter, connection. This connection will represent that channel between the client and the server. This allows me to then take it and then observe things on it. So I'll say connection.onMessage. This allows me to look inside this channel and then see when messages arrive from the client to the server. When a message arrives, I know it's coming from the client I just built, and I know what kind of messages that client is sending. It's sending messages that contain the following properties: event, type, data, from, to, and room. Because I know the type and the shape of the message, I can go ahead and convert it from this raw payload to a JSON. After this, I'm free to treat it as a JSON object, and that makes it easy to access the properties directly. So the next step is to decide what to do about this message. Now that we have a JSON object here, we can conveniently look at property here, and the property is called event. So message.event, it tells us what to do. So if message.event equals to ready, it means the client is registering. It means we need to save the connection for future use. So that's what's going on here. If message.event equals signal, that means it's a signaling message. That means the client had already registered and it's ready to do some signaling. So we will do some signaling logic here. If message.event equals to log, that means it's a logging message and we preserve that log. And this is going to be used later to build the sequence diagram. If message.event equals get logs, that means our debugging tool, the tool that visualizes sequence diagrams, is requesting all the log messages, so we'll just go ahead and send those log messages. Let's have a look at what happens when a client is registering. So a client registering means that I need to preserve that connection object that represents the link between the signaling server and the client. So how do I preserve that? Well, I need to know what client this link belongs to. I like to think about this connection as a linkage between signaling server and the client. So what I do is I look at the message, and the message will contain information necessary to determine what client it's coming from. So it'll be a message from to get the ID. So from our demo, that would be PC. So the first client that registered was PC. So message.from would be equal to PC in this scenario. And then the other thing I'm looking at is room. So room would be room 1. That was the room that PC used when it was registering. What I need to do next is to customize my connection object. So the connection object needs to be such that I can later fetch it and recognize it. So to do that, I add client ID and room ID as the properties, as the additional new properties that connection did not originally have. So I do this, I assign the appropriate values, and then I save this. I don't save it in the database. I actually don't need to do this. That's not the scope of this project. For the scope of this project, it's sufficient just to have a local object where I'll just save key value pairs. So the key in this object is going to be the rooms. So room ID in this particular case will be the key that will represent the room where this connection will live. So originally, when I first connect my very first client, clearly there are no rooms. This is completely blank. So in that scenario, this if statement here will be true. The logical question that we're asking here will have a positive answer, meaning if there is no key equal to room 1, the answer to that is yes. Therefore, I will do this. So it assigns a value to this key. So the key here is going to be room 1, and then the value is going to be an empty set. Once this has happened, I know for sure that by the time I get to here, room 1 is a valid key for this object. And then I can grab the set and then insert my connection into that set. So at this point, by the time I get to here, I know that I have already preserved this connection, and therefore I can announce it. So here I'm announcing this fact that a new client was connected to the signaling server. So this will happen for every new client that connects to the signaling server. So what happens when a signaling message is sent? When I receive a signaling message, I want to forward it. So if the properties that I need are all there, and if message.to is present, then I go ahead and forward the message. So the way I forward it is I just look at the message, the room it's trying to go to, and then I check the connections in that room. If I find a connection that matches the destination that this message wants to go to, then I just send that message using connection.send. This is something that WebSocket just gives me. So I stringify the message and I just send it. A step before that is me logging this. So I also log this event, but this is optional. The core part here is this sending the message. The log will just preserve this for me so that I can later visualize this in the sequence diagram. So what happens when I receive log messages? So in addition to logging internally like this, I also receive external logs from the clients. When a client sends me a log, message.event will be equal to log. So then I know what to do. So I just add a logging message, and it's going to be the same exact way like I did it internally, meaning the add log helper function takes a message as a parameter, then it just saves it. So how does it save it? It saves it the same way, very similar, not same, but similar way to how I was registering clients. I have an object here, logs, and it's an empty object. And then what I do is I preserve the logs based on what room they're coming from. So I will check if the room from which the message is coming from exists. If it does not exist, I will create an empty array for that room. So the key will be the room ID and the value will be the array. And then I will just push all the logs into that array. Later on, when the client is requesting to get those logs, meaning my sequence diagram client, the client that is specifically doing sequence diagrams, when it's requesting it, I will be able just to send the list of logs from the particular room it's requesting. In fact, that happens here. So get logs. So if a message that I'm receiving is such that message.event equals to get logs, it means it's coming from that page where I'm rendering the sequence diagram. What I do here is I just say connection.send, and then I stringify all the logs from the particular room the request is coming for, and then I just send it. And this will then allow the client to render the sequence diagram. And finally, I almost forgot to mention that broadcast to room works very similar to forward message. So broadcast, first of all, broadcast only happens when a new connection is received, and then the message is broadcast to everyone in the room. So the way it works is it's similar to forward in the sense that every connection is looked at in the room, except unlike forward message where a particular connection is picked and then used to send a message, here every connection in the room is looked at and then a message is sent. In fact, I happen to be omitting the original connection just because I did not want to broadcast the message to the client itself that triggered the need to broadcast, but it's just my preference. It could be set up such that everyone gets it in the room, but that's the idea. Go through every connection in the room and then just send a message on each connection. This highlights the importance of preserving the connections, because by tagging the connections with the client ID, by tagging the connections with the room ID, I can do things like this. I can go ahead and search for every connection in the room, and then like in the case of forwarding, I can then look at the connection client ID. And this is only possible because I tagged it. If I did not tag it, I just wouldn't know who that connection belongs to. So this is very, very important to correctly register and preserve the connections when they're coming in. Let's have a look at the front end code. So app.js is where everything happens when it comes to the front end. All of the logic lives here. This is a lot of code. This is over it's actually exactly 600 lines of code. So there's a lot to go through here. And so to make it a little bit more digestible, let's look at this. Let's look at the sequence diagram and then use it to refer to code. So the first thing that happened was PC registering. And we saw how the signaling server receives that message and then deals with it. However, how does PC actually send this message? How does the client side how does it know how to send a signaling message? So let's have a look at this. So I have a button here, register, and then I added a click listener on it. And then the way I handle clicks is like this. So I grab the signaling IP value, and then I put it inside this app state object, which has all the important things I care about, such as signaling server instance, signaling server URL, local stream, wake log, user ID, room ID. I'll get into these a little bit later, but I keep it all here. So my application state lives here. I define the signaling server URL here. So I grab it from the input. So the signaling server IP is my input from the HTML piece. So I grab the value from there and then I save it in my app state object. What I do after that is kind of interesting because I'm immediately requesting the microphone access. And the reason I'm doing it this early is because I decided to associate the act of requesting microphone access with this button. And I do this in order to satisfy the iOS requirement where you can only request microphone access when there is some explicit user action. You cannot trigger it because of some internal logic on the front end code. It has to be tied to user action. If you don't do it this way on iOS, you will never be able to get microphone access. So that's the reason I'm doing it this early. So once this succeeds, it means that the user saw a request to give microphone access, and so presumably at this point, user has provided access to the microphone. The steps after that are as follows. So I'm grabbing the value for user ID and room ID. So again, these are HTML elements, so user ID, room ID. I'm grabbing those values and then I'm updating my application state object. Once this is all done, I'm ready to initiate my connection. Connect is where I create my WebSocket connection. So I create an instance of that connection. I pass appstate.signaling server URL as the parameter, meaning I pass the URL to the signaling server. So the WebSocket is built in the browser. I don't even have to import anything. I just say new WebSocket. That's part of the browser API. That's kind of cool. This creates an instance of this WebSocket connection, and then I associate it with appstate.signaling server. This means my application state object will have that WebSocket connection saved in it. Later on, I can access it and do things with it if I need to. In fact, I'm doing it right here. So what happens here is I am observing the unopen event, meaning when the browser successfully connects to the signaling server, I want to do certain things. Now what I want to do here is send the registration message. So once there is a successful connection to the signaling server, I immediately create a payload that will allow me to register this web app instance with the signaling server. So I form a message, I put all the correct properties here that will be interpreted correctly by the signaling server. So this is the piece where the signaling server receives a message and then registers the client. That's the piece here that will be triggered. In the payload, I put event as ready. I put the type, put where it's coming from, meaning I put the user ID, and then I also put the room ID. These are important, and this is important because those are the three things that I'm looking at here on the signaling side. Once this payload is formed, I then send it. Also, prior to sending, I'm logging things. So I'm doing this internal logging where the logs are displayed in the browser, and also I'm doing this centralized logging where I'm sending a log message to the signaling server so that later I can build out the sequence diagram. So that's how I connect to the signaling server. What I did after this was this. On phone 1, I tapped on add connection, and then that produced a widget. Inside that widget, I specified the target ID. In this case, it's PC, and then I tapped on the connect button. And then very quickly, a connection was established between phone 1 and PC. So let's have a look and understand how this all worked. The first event that was logged in this sequence of events was this: created peer connection with target PC. So let's understand how this part is done. So this entire process starts with this button, add connection button. Let's have a look at it. This button has an event listener that listens to click events. And then inside the handler here, I'm doing two things. I'm building a connection widget, and we saw that in a demo. There was a widget that was built, and then I am appending this widget to the connection list. And also in the demo, we saw that when PC received 2 connections, there were 2 widgets. So this app can let you have as many connections as you want within reason. And for each connection, there will be a widget. And so there is a list of widgets that will be displayed. And that's what this connection list is doing. It's a list that lets you stack a bunch of connection widgets. Let's have a look at inside this helper function here that builds this connection widget. It takes a parameter, and in my case here, I am sending null, and this parameter represents peer connection. So there's 2 scenarios. Either there is an existing peer connection, and then the job of this widget is to visualize that existing connection. For example, that happens when there is an incoming connection. Or this widget is used to create a brand new connection, and in that scenario there is no existing peer connection, so this would be null. What's going on inside this function? So the job of this function is to build that widget. This widget has several UI elements. It has its outline, and also it has this input for the peer ID, so that's going to be done here, and then it needs to be like with the proper placeholder and all that. And then there is also the button, right? So there's going to be a button that I tap on to initiate the connection. And so depending on the situation, I will visualize the button differently. Let's look at the scenario where I'm creating a brand new connection. So that scenario is when this is null, therefore this if block will represent that particular scenario, because this will be equal to true. What I'm doing here is I'm creating a new button, and I'm labeling it as connect, meaning I'm about to do a connection. And then I'm assigning a handler to this button. So when the button is tapped on, this will happen. So what's going on inside here? I'm grabbing the peer ID value rather. This is necessary because in order for me to establish a connection, I need to know who I'm establishing this connection with. Therefore, this is a must. So I grab the peer ID value, and then I make sure it's not null, and also there is no prior peer connection. And if these conditions are true, then I initiate my peer connection. Now, there's a lot going on here. In fact, what goes on here is going to affect things below here. So briefly, when I initiate peer connection, there will be a peer connection object that will be created, and then it will be saved inside a map. I have a map that lets me keep track of multiple connections. And again, in the demo, we saw how PC had 2 connections. Any client can have multiple connections, so there is a need to keep track of multiple connections. The way I accomplish it in this code is by using a map. So peer connections is a map, and this map allows me to have this key value mapping situation. So in this case, the key will be my peer ID, and then the value will be the object, the peer connection object. Here, inside this function, I will create a new peer connection, and I'll save it inside that map. So by the time I get here, I know that that map already has the peer connection object saved. That is why I am grabbing it from there, and I am then assigning it to this formerly null value. And then the reason I'm doing it is because my goal is to immediately, as soon as this widget is built, to associate the widget with the peer connection. It's important because this peer connection might disappear or it might disconnect it. There are scenarios where I need to handle disconnect events. When a peer connection is disconnected, I then need to find the corresponding widget and deal with it. So to make it easy, what I'm doing is I'm expanding this peer connection object by just adding this new property .widget. This is not something it comes with. This is something I'm adding to it, and this way I can conveniently track the widget that corresponds to this peer connection. This is something similar to what I did inside my signaling server when I was expanding my connection objects with client ID and room ID. It's a similar idea, except here I'm expanding it to have this widget association. At this point, my peer connection is built, and then the widget is associated with it. The next thing to do is to have a look at the function here, because there's a lot of important things going on here. The first thing to notice is this parameter target ID. So I'm creating my peer connection with the target. And what's noteworthy is I'm first checking whether there is an existing peer connection object out there. There is a scenario where this object already exists. That would be a scenario where I already, as a client, I already received audio, an audio stream from the peer. And what I'm trying to do is I'm trying to use this existing connection through which I'm receiving audio to then send audio back to that client, to that peer. And that's the scenario where this wouldn't be null. However, in this scenario that I'm describing right now, where I'm initially calling from phone 1 to PC, where I'm trying to establish the connection from phone 1 to PC, in that scenario, this would be null. Therefore, this needs to happen. And so what I'm doing here is I'm calling this helper function called create peer connection. It's a pretty involved function, very important. I would say this is like the core of the WebRTC process that is happening in this front-end code, and I'll get into this. But the point of this function is to produce this peer connection object and then return it. And then I'm grabbing it, and then I'm saving it in the map where I have my key and then the value. This is important because this allows me to access this when I need to, using just the target ID. The next step after that is to pair this peer connection object such that it's ready to be sent as an offer to my peer. The peer is going to be PC. So phone 1 is preparing the peer connection object. By preparing, I mean it's adding things that the peer connection object needs to have, and then it will send an offer to PC. What does that mean to prepare the peer connection object? It means multiple things. Number one, adding the audio to it. Initially, when I registered phone 1, I tapped on the register button, and that button created this request to get microphone audio, and then that was saved in the application state's local stream. So it's already here. By the time we're getting to this line of code, the microphone stream should already be available and ready to be used for the audio streaming. So what I'm doing here is I'm getting the first track out of this stream. In general, this could be audio plus video. This could also be audio that has multiple tracks. There's different scenarios. In this scenario, I only use a microphone and there's only one track. Therefore, I'm just getting the first track. I have my track. I make sure it's not null. I'm able to get it. Once I'm good with that, I am adding it to the peer connection object. So the peer connection object has this function called add track. So I'm adding this track. I'm also mentioning the stream where the track is coming from. So this is all browser API, like add track and all the things related to the peer connection. That's all browser API. I'm doing this. And then what's noteworthy, in the sequence diagram, there's a corresponding log message. So this log message here, added audio to be sent to target ID, is right here. Before this message, before this event, there is created peer connection with target PC, and that is coming from here. And I'll get into this in a moment, but that's the sequence of events. So created peer connection with target PC coming from here, and then I'm adding the audio track. So that's here, and the corresponding log is this. And then the thing that happens after this is ICE negotiation needed with PC. And I'll get into this too. I'll explain why this is happening, but it's triggered by this. So after the audio track is added to the peer connection, there's enough information already available on phone 1 to send an offer to PC and then kick off the process of discovering each other. What I'm doing here is I'm creating this offer object. So this is done using the built-in function from the WebRTC API that produces this offer object. This is kind of like a draft. Between this line and this line, there is a chance that I could modify the offer if I chose to. I could tweak it. So this offer contains information about how phone 1 wants to send audio, what port it's going to be available on, what kind of audio it's sending, what kind of bitrate, what kind of temporary fingerprint it's going to use for the secure connection that will be established between phone 1 and PC. It also includes information about the networking that it already knows about. So phone 1 already knows its local IP address. So I'm running phone 1 on my Wi-Fi, so it knows its local IP address. So it will also include that information. So that is the bare minimum that is available. Because I choose not to modify this offer, I immediately commit to it. Setting local description with this parameter is an act of committing to this offer, or another way of thinking of it as a contract between phone 1 and PC. So I'm committing to it. And so I'm setting it as part of the peer connection object. And after this, I am ready to send this information to PC. And the way I'm doing it is using my signaling server. So I'm creating this JSON that has information about where it's coming from, what kind of event I'm trying to communicate, what kind of type, what type of a message I'm sending, what room it's going to. So the usual things. And then the core payload here is this, is the data. What it is the contract. So I'm extracting the offer information out of the peer connection object. And this is how it's done. So it's pc.localDescription.sdp. SDP offer, that's what it is. Session Description Protocol, that's what it stands for, SDP. This information is going to be sent here, right here. So I'm going to use the signaling server to send this information. If we look at the diagram, this is what's happening. So SDP offer being sent to PC, and it gets delivered to the signaling server, and then the signaling server pretty quickly sends that SDP offer, forwards it, this SDP offer to PC. So that's what's going to happen. Now, before I dive deeper into it and explain how the peer connection was created and what ICE negotiation is all about, I need to mention quickly what this is. So after I sent this payload, what I'm expecting is that the audio connection will be established rather quickly after this. This is a convenient place for me to request the screen to stay on. And I'm doing this in order to allow mobile devices to keep their microphones on. If the screen goes dark on a mobile device, the microphone also stops working, and that's not convenient. It's done using this browser API. So I say navigator.wakelock, and then I request screen to stay on, and then the mobile device gets this through the browser API, and then it communicates it with the operating system. The operating system respects the request to keep the screen on, and ultimately the screen stays on. Let's have a look at the helper function and then demystify as to why this is happening in this particular sequence. So here's the function. And the first thing that is happening in this function is this. I'm calling the built-in API. I'm calling the constructor from the built-in API that is part of the web browser. So I have this access to WebRTC functions that I need, and this is the one I need to create a peer connection object. This is a very important object because this object is going to represent the connection. So there's going to be a lot of things happening with this object. In this example, I'm creating this object on phone 1 first, and then PC, once it receives the offer from phone 1, it will create its own peer connection object. So peer connection object is how the web browser, or the client that runs in the web browser, the app that runs in the web browser, will maintain its connection and then do the connection bit. All of that will be happening through this. So this is very, very important. I'm creating a brand new connection. I pass this configuration, and this will make a little bit more sense as I dive deeper into it. But just for now, I'll mention that this configuration contains a URL to a stun server, and I'll explain what it does. This configuration could have more things. I have a minimal configuration, and in some cases you can completely skip it. It can use the default values for this configuration, but I have to use it, and I'll explain why I have to use it. I'm creating this object. Then I'm tagging it. The idea is to add a property and then add a value that makes sense to me. In this case, I want to mark it with the ID of the target. So in this particular example, this would be PC. I want to mark it such that I know that this peer connection is between me, in this case, phone 1, and PC, which is the peer I want to connect to. Just to illustrate why this is important, inside this helper function, once the peer connection object is created, then there are several listeners, event listeners set up for this peer connection object. These listeners are here to listen to the WebRTC specific events that are occurring with this peer connection object. And so it's super critical to know when these events happen. And it's also critical to know which peer connection object these events are happening on. Having this underscore ID with some kind of meaningful information that will be stored here, in this case, target ID is what makes sense to me. Having this helps me a lot to know that when, let's say, on connection state change happens, and I'll get into this later, what this represents, but this is important for me because I can see immediately which peer connection it's happening on. I don't need to do anything complicated. I don't need to infer anything. I can just directly look at pc._id and then use it either to log or to do something interactive. The thing I do after that is this. I'm logging this event, and that's what this is, created peer connection. Then, like I explained earlier, I am doing this. So I created the peer connection using this helper function, and then I added my audio. And at this point, and this is part of the WebRTC process, this is something that is normal to it. So then I'm adding audio to this peer connection. I'm sort of loading it up with the things that it needs to do. And this event, adding this track, the audio track that is coming from the microphone of phone 1, this event means that this peer connection is ready to do the next step. It automatically triggers the next step. And so from the diagram, from the sequence diagram, this is happening right after audio is added. So this is the next step. And to make sense of it and to understand what this is, like what ICE stands for in this case, I need to dive a little bit deeper into WebRTC and what it's trying to do. So in simple terms, WebRTC is concerned with two things. One is dealing with media, which means grabbing it from the device, chopping it into small pieces, using the network to send it in an efficient manner so that the other peer can receive it, reassemble the pieces, and then produce the media experience for the consumer. So that's one concern. And the other concern is to connect the peers and to have this reliable peer-to-peer connection that we want in order to send audio and video with low latency and good experience. Let's talk about this aspect of WebRTC, which is about finding the peer. So this is what's happening here. ICE negotiation needed with PC. This is happening right after the multimedia piece is pretty much done. So the number one concern, or the first concern, which is about multimedia, is done. At this point, we grabbed the audio track from the device, we prepared our peer connection object, and it thinks that at this point, the next concern it has is about networking, it's about finding the peer. How does this work? How do peers find each other? In normal situations, the peer would be running, let's say, on a home Wi-Fi network. So what that means is the peer, let's say phone 1, only knows about its local IP address. So the IP address that it has at home, the home Wi-Fi IP address, which usually means it's some kind of address that starts with 192.168.something.something. That is not very helpful if the peer is not on the same network. this would be the challenge to solve, which is two clients behind their home networks or work networks or some kind of network where their IP address that they know about is not useful outside that network. So how does that problem solved? Well, that's where this comes in. So as soon as audio was added to the peer connection object, the WebRTC process immediately triggered this ICE negotiation needed with PC. So let's have a look where it happened and then understand why it's happening. So ICE negotiation needed. So this event is triggered. Now, I'm not doing anything except logging. This is on purpose because I don't really need to do anything here, but I need to log it in order to build a comprehensive sequence diagram because this is a very critical step. So what this step means is phone 1 is going to take a series of steps needed to discover itself on the internet. And that's what this stands for. So ICE in this case stands for Interactive Connectivity Establishment. So it's a technique, and it's a very simple technique. This technique is pretty much just this. You will, as phone 1, you will go to this server and you will ask this server, what is my IP? So you will use a certain port as phone 1, and you will ask, what is my IP? And that IP will be the one that is used on the internet to represent you. So it'll be a combination of the IP and the port number. Obviously, at home, there's multiple devices. Those devices will share the same IP, but the way that particular device, that particular application will be distinguished is going to be by its own port number. That server will respond with that information. So then that information is going to be used for phone 1 to learn about itself. Every time phone 1 learns about itself, like it learns about its IP address and its port number. It also learns about its own IPv6 address. It learns about its other IPv6 address. It learns about the ways it can be discovered. So it's trying to gather as much information as possible about how it can be discovered. In fact, there is even a situation where there is no public IP and port combination that can identify phone 1 on the internet. There are situations like this. For those scenarios, this is not enough. Providing only the stun server is not enough. There will need to be another server, another URL to a server whose job is going to be to relay the communication. So it'll essentially act as a proxy where the peers will talk through it, and then they will receive information from that server. So I'm considering only the cases where peers can discover each other, where peers can discover each other's combination of IP and the port number. It makes it very contained. I will not rely on that server to relay the communication because that server will be, like having that kind of server is not trivial. If they're going to cost money, or I would have to run my own server, the use case for that is going to be quite limited. For the scope of this application, I decided to eliminate it, but I have to mention that there is a situation where it's impossible for phone 1 to learn about its IP and port combination that can be used to find it. So phone 1 is learning about where it is on the internet, and the goal is to tell PC about that. And that's what we're seeing here. So this is the announcement of that process. So it starts triggering that process. There's something else going on here. So here we see that phone 1 is sending SDP offer to PC. That is related to these steps. So there's two things happening at the same time. On the one hand, I created the peer connection object, and on the other hand, this got triggered. And those two things are happening asynchronously. So why is SDP offer being sent so quickly? Why it's not sent after phone 1 learned about its presence on the internet and after phone 1 learned about how it can be discovered by PC? After audio is already added to the peer connection, it's already enough information to be sent to PC to trigger the process. So the initial SDP offer, and by the way, we should have a look at how it's done. So the SDP offer is sent right after the track is added. So once the track is added, we are sending the SDP offer. I'm sending it here. using the signaling server. Right before that, I'm saving this log, and that is what's here. That's what's happening here. This gets sent to the signaling server, and then the signaling server receives it, and then quickly after that, it forwards it to PC, and PC receives it, and then PC will have to deal with that too. Parallel with that, this is happening on ICE gathering state callback called PC. So this step triggers this step. And so there's two things happening at the same time. So while this offer was being sent, ICE negotiation, ICE gathering started happening. It's noteworthy that this initial offer actually contains something about networking as well. Phone 1 already knows about its local IP, and it will include that information in the initial offer. However, this ICE negotiation process that got triggered will gather more information with relation to networking. On ICE gathering state callback called PC, where is this log coming from, and what is it going to tell us? Obviously, this is happening with the peer connection object. So let's go and have a look at all the event handling that is going on here. So it's coming from here on ICE gathering state. Again, I'm not doing any actions here. I am just logging it for the sake of understanding the exact sequence of what's happening with WebRTC. What's the step after that? What's happening after this? I get these. Received ICE candidate, received ICE candidate, received ICE candidate. So I received 3 ICE candidates. The ICE candidates represent different information about how phone 1 can be found. So that information can be about IPv4 public address with the port number, IPv6, and there's multiple IPv6 addresses that can be used. So it's going to try to find as much information as possible. Where is this happening and why it's followed by this? So let's have a look. There's the sequence, right? So received ICE candidate, sent ICE candidate, and then sent ICE candidate means the payload that presumably contains information about this ICE candidate is sent to the signaling server, and then that is then forwarded to the target, which is PC. And that is happening several times. So this is the first time, then this is the second time, and then this is the third time. So received ICE candidate. Let's have a look. Where is that happening? On ICE candidate. So it's happening in this handler. So that's where I'm logging it. So what I'm doing here is I am looking at the information that came with this handler, and then I am making sure that information is not null, and then I'm creating a payload to be sent to PC using the signaling server. So I am creating this payload, putting the information. The crucial bit here is this information that is going to be converted to a string. And then I'm going to put it like this and send it to the peer. So it's rather straightforward. And so this information will be sent to that peer, and that peer will then use that information to inform itself how phone 1 can be discovered on the network. That's the purpose of this information. And so when I send this, right before that, I'm putting this log here that says send ICE candidate to, and then I specify the ID, and that's what is happening here. This log is coming from that line of code, and then it's forwarded to the signaling server. Okay, so what's going on with PC? So it receives this SDP offer. This SDP offer contains information about how phone 1 wants to send audio or video, what format, what bit rate. Also, it specifies the security information, like how it wants to encrypt it, what kind of standard it wants to use. So that's what's going to be included in this payload, in this message that signaling server forwards to PC. And then in addition to this, phone 1 sends a bunch of ICE candidates, and ICE candidates will help PC learn about how to find phone 1. A lot of important things are happening here. So before diving into the code, I need to explain the WebRTC logic behind it all, like how WebRTC operates in order to make this connection happen. So the way I wrote the client-side code is such that if it receives an SDP offer, it implies that a connection needs to be created immediately. The response to this SDP offer is this: creating a peer connection. So again, similar to phone 1, where there was a widget that led to this creation of the peer connection object, here a widget will also be generated, except the order is different. The peer connection object is created first, and then the widget is created. The widget is going to be simpler here. It will only contained the disconnect button and then some labels to explain what kind of connection it is. In the case of phone 1, the widget also contained the connect button and then an input field. So it was a little bit more complicated widget, but in both cases, the widget is created using the same helper function. And then another important step is this: received audio track from phone 1. So what this means is PC acknowledges that SDP here is trying to announce that audio will be sent from phone 1. And so it's preparing for that. So it will prepare the browser. So it'll change the UI, it'll add the widget for audio, it'll prepare everything to start playing the audio. So it's pretty much just pending the part where the information is received that'll contain the audio from the microphone. So everything else is ready at this point. And then we see these. So these are the logs that are triggered because of the candidates. So phone 1 is sending a bunch of candidates, and that is happening asynchronously. So the logic that is related to the SDP offer is running in parallel with the part where candidates are handled. That is all happening asynchronously. So the events can overlap in arbitrary order. So once a candidate is forwarded from the signaling server to PC, then PC says that it receives a message, and then it acknowledges that it's a candidate, and then it adds that candidate to the peer connection object. So the peer connection object is here, and it adds it to it. So by doing so, the peer connection object is expanding its understanding of how phone 1 can be found. Initially, the SDP offer, which is what informs the peer connection object, this is only aware of the local IP address and the port number of phone 1. And once the ICE candidates are received, that creates more knowledge about how phone 1 can be found from outside the local network. This could be IPv4 plus port number, could be IPv6 or another IPv6, so it could be multiple things. Again, so each candidate is processed like this: a log to just acknowledge the receipt of the signaling message, a log to acknowledge that it's a message of this particular type, and then the candidate is added to the peer connection object, and that repeats itself. Then this is happening. This is very important, and this is related to this. And also it is related to this rather. So PC is sending an answer to phone 1. And this answer, the fact that an answer is sent implies that the offer that PC received is acceptable, meaning it can handle the same audio format that phone 1 wants to send. But this is not guaranteed. Like, it's possible that phone 1 could have said, I want to send you video, but PC does not handle video. So if that was the case, it would reject the SDP offer. Or if phone 1 sent video plus audio, PC would say, I can do the audio bit, but not the video bit. So in that case, the answer would have been semi-positive. However, if it was just video or audio that is not of a format that PC could handle, PC would not send an answer. It would actually throw an exception. It would throw an error when it tried to apply this information to the peer connection object. And then it would be the developer's job to handle that. And there's different ways to handle it. One way to handle it would be to send a signaling message to phone 1 and inform it that, hey, whatever you're offering is not acceptable, let's do something about it. And then it's just a matter of deciding how to handle it. It could be some kind of information to the client, to the user, to maybe change some settings, or maybe switch to a different browser. It would be something where human intervention would be necessary. Now, in this demo, everything is working well. There is no need to worry about it. So it's rather simplistic. So this is being sent, and then it's being sent to the signaling server. The signaling server forwards it to phone 1. Then we see here that the second ICE candidate is added here. So the first one was added here. The second one was added here. Okay, and then so what about this log? Because PC sent its offer to phone 1, it implies that phone 1 knows that PC is happy to accept the offer and do the connection. Therefore, phone 1 needs to know how to find PC. So PC starts learning about how it can be discovered. So it initiates the ice gathering state. So it's it's actually the exact same thing that is happening here when phone 1 started gathering its ice candidates right after it sent its offer to PC. So the same exact thing is happening here. It sends an answer to the offer and then starts gathering ice candidates. And those ice candidates will be received just like they were received on phone 1. And then PC will be forwarding them to phone 1. And that's what's happening here. Now, together with that, this is happening. Ice connection stage change for IDPC. And this is also very, very important. So this means that PC is ready to test out the candidates that it received for connecting with phone 1. So it received some information about how to connect with phone 1 in the form of ice candidates, and then it begins testing them. And that's what it stands for. Ice connection state change means that it begins testing them. And in fact, the same thing is going to be called here, ice connection state change for phone 1. So once phone 1 receives an answer, it starts testing the ice candidates. And also it receives ice candidates here, and it begins testing them. The answer here will actually contain the initial information about where PC thinks it is. So it will send its home Wi-Fi IP address because that's what it will know. So it will contain that in the answer. And so phone 1 can immediately begin testing that initial information. And then it'll test the other candidates too. So that's really what this signifies, the beginning of the testing stage. So ice connection state change for IDPC, ice connection state change for phone 1. After this, they test the ice candidates, they find the good one that works for them, and then they will update the ice connection state change one more time. So it's happening here, the second change of the ice connection state. So that's the second time it changes here on PC. So first was when it did the testing, and the second one is when it concludes that the connection is successful. And then the same thing is here. So on phone 1, it begins testing, and then it announces that it's done here. So the second one is happening here, ice connection state change for phone 1. And then what's notable here is that right around this time when the connection is established, by the way, as soon as the ice connection state changes to established, connected, this happens. So peer connection established, and then it's a arrow that indicates that there is a peer-to-peer connection. So it's happening from both clients. So from phone 1 to PC and from PC to phone 1. So at this point, the WebRTC connection has already established. And then so the signaling is no longer really needed because they can talk to each other directly. And so at this point, the audio stream is being sent. The data from this connection will be fed into this, whatever we prepared for the audio track. It'll be fed into here, and then we can hear the audio. And that's what happened in the demo. Now, what I want to mention regarding this stage, so right around the time when the peer connection is established, the last ICE candidate that is received is going to be null. So the null ICE candidate means every single ICE candidate has been explored. And so that's usually happening right around where this happens, where the peer connection is established. At this point, the connection between PC and phone 1 is established. And then in the demo, I began this. I registered phone 2, and then I started a connection between phone 2 and PC. And then the sequence diagram shows that it's going to be the same exact thing that happened between PC and phone 1, the same exact sequence of steps. The same exact steps, perhaps slightly out of order, slightly different order, because the ICE candidates are received in somewhat arbitrary order, and the way that interplays with the SDP related activity can be different. But overall, it's going to be the same exact situation between phone 2 and PC. So at this point, it's time to dive into the code and make sense of how the code was handling these important WebRTC events. PC receiving the SDP offer and then reacting to it. So what happens? How does it do it? because it's coming in from the signaling server, it's going to be a message, and indeed it's a message, signaling message, and then it's processed in this handler function that produces this log. So let's have a look. The signaling message code is here. So once the signaling server is set up, we have this on message handler that receives payloads from the signaling server. In that particular case where the SDP offer is received, the message type is going to be equal to this, so SDP type. So there is a handler for that. Let's look inside this handler. This handler receives the message as the parameter, producing this log, and then I'm checking if the connections map, so each peer connection object is saved in a map, and so I'm checking if there is an existing peer connection saved there. If there is no peer connection saved there, then it means it's a new offer from a new peer, and I am going to create the widget. So I'm building out the widget, and it's very similar to what happened with phone 1, except here the difference is the build connection widget helper function is called with this parameter. And the parameter here is creating a brand new peer connection. And so we already saw this helper function, how it works. It returns a peer connection object, and then it has a whole bunch of handlers set up on the peer connection object. And because this returns a peer connection object, so the way a build connection widget will work for this scenario is slightly different from the scenario with phone 1. And with phone 1, this was null, because with phone 1, the widget that was created was intended to trigger the connection of the peer connection object. But in this scenario where PC receives an SDP offer, it builds the connection because it does not need to manually trigger it. It knows when to create the peer connection object. So it builds it out, passes it as a parameter to here, and then the difference from the example where I explained how this works with phone 1, the difference here is instead of this block of code, it's going to involve this block of code. So here, peer connection is not null, therefore the widget is going to be different. It's not going to have this. It's not going to have the button, and then the corresponding handler for the button that was initiating the creation of the peer connection. So here it's a lot simpler. So I'm saving the peer connection in the map, and then I'm assigning this key to it. So the key value pair is going to be this. And then I'm building out the widget, setting the label, and then I'm also adding the ID value to the connection element to make it easier to find. And then also I'm setting the log here. Sending the log to the signaling server. At this point, we know how we got to this. Then the next step is this. So where is this coming from? Received audio track from phone 1. This is coming from the WebRTC events. So at this point, the widget is created and it's right here. And then this helper function also saved the peer connection object in the map. And so what I'm doing next is I am saving the widget in the list of widgets because PC can have multiple incoming connections. And in the demo, we see that it has phone 1 and phone 2 both connect to it. I need to have a list of widgets for that. And then here, I'm grabbing the peer connection object from the map because by the time I get here, the map should already have the peer connection object inside it. And so the reason I grab it is because I want to do this. I want to expand the peer connection with this attribute widget and then assign the connection element to the widget. This way, when something happens to the peer connection, I can grab the corresponding widget and then possibly remove it. When the peer connection gets disconnected, I immediately remove the connection element, and this makes it easier. So what about audio? So in the sequence diagram, we see this received audio track. The event that happens after the widget is created is this one. Received audio track. Now, this is not coming from the signaling server. This will not be handled where the signaling message was handled. So this will be somewhere else. So where are the WebRTC events handled? They're handled in here, where the peer connection is created. So I have a whole bunch of handlers here for various events. And then the one that triggers that log is this one, on track. So here, an event is received, and this event announces the fact that the SDP offer contained information about the proposed audio. And so what PC is doing here, and by PC, I mean the client PC, not this variable here. This peer this client named PC will receive an audio track. And I'm checking and I'm making sure this is the right kind of audio track I'm receiving. Then I'm grabbing the widget because I need to add this audio playback UI to this widget. And so if for some reason the widget is null, that's a problem, and I make it obvious that it's a problem. I produce a log in the browser. So if everything is okay and the widget exists, then I produce this log, and this is the centralized log that goes to the sequence diagram. These logs do not go there. These logs stay in the browser. And so the next step is to create the audio playback widget. It's a very simple built-in widget, comes from the browser API. It just has the play pause button, audio, it has the volume adjustment, and then has the timer, and then I think a seek bar. Those are the things that I'll have. So I'm setting it up. Then I'm creating a stream, again, browser API stuff. So a new stream object. I'm adding the track, and the track is going to be the audio track that is coming in from phone one. So I'm grabbing that from this object here. So this is the parameter that WebRTC gives me inside this handler. Very convenient. So I'm grabbing it from there, passing it, I'm adding it as a track to the stream so that I can grab that stream and assign it to that UI element that'll represent the audio playback. So it's done here. And then finally, I grab my element, my widget, and then I'm adding this audio playback element to it. And that's it. And also, I'm doing this. This is, again, I mentioned it earlier, this is about making sure that the screen stays on. This is relevant for mobile devices. You want to keep the screen on in order to keep the microphone on. On mobile devices, if the browser is the only means you get the microphone access, then you have to keep the screen on. Otherwise, the browser will pause the microphone once the screen goes dark. That's how the on track is done. Let's move forward. So what's happening after that? A bunch of candidates are received. So these candidates that are received, each of them is coming through as a signaling message, and then that candidate is received and then added to the peer connection. So what does that mean to receive a candidate and add it to the peer connection? Let's have a look. It starts with a message. So let's go up and look at how messages are handled. So this is our message handler. We receive a payload. This payload will contain the ICE candidate because phone one is sending ICE candidates to PC. So the handler for that is going to be this one. So the message type equals to candidate. And then let's have a look at what's going on here. So the message will contain the candidate information. I grab this candidate information. That information is about how to find phone one. Basically means IP and then the port number. That's what we care about. So what am I doing here? I'm making sure the message has all the information that I care about. And then I'm grabbing my peer connection that corresponds to the peer that sent me this message. If I have multiple peers sending me messages, I will be able to handle it. So I'm grabbing it here from the map, the exact peer connection, and then I'm adding the ICE candidate to this peer connection. So this function comes with the WebRTC API. It's part of the browser. So I'm just calling it. I'm wrapping this payload into this RTC ICE candidate, and then I'm adding that ICE candidate in this way. The way I'm doing it is prescribed by the WebRTC API. So at this point, the peer connection knows about this particular ICE candidate. PC will receive more ICE candidates, and it'll repeat this process. It will do this for every ICE candidate. What's going on after that? So the next important event that happens is this one, send answer to offer from phone one. And this actually takes us back to the function that was doing this. So let's go back to that function. So that was done here in handle offer. Once this is done, once the peer connection is created, it means I can do things with the peer connection. So the first thing I do is I set remote description. This is a WebRTC API function that allows me to save the remote information, the remote offer information. This peer connection object encompasses everything. The information about the clients, connection, what it can do, what it can handle, the remote peer information, and then that also includes the ICE candidates. So there's all of that is contained in the peer connection. That's why we are doing this. And that's why I'm doing this. I'm setting the remote description in order to build out this peer connection so that ultimately it can establish a successful peer-to-peer connection. The step after this is to produce an answer. And it's very similar to how I was producing the offer that was sent here from phone 1. So I say peer connection.create answer. It produces this draft answer. I have a chance to tweak it. If I don't like something about this answer, I can override it. I can change some sequence of things, order of things inside the answer. In this case, I choose not to do anything. I just take it as is because my case is rather simple. And then I commit to this answer, and that is doing this. Set local description. This means that the peer connection's local description, essentially things it's willing to do, the things PC, the client named PC, is willing to do. Like phone 1 might have said, I want to do both video and audio. And PC would say, I can only do audio. And then the answer would be such that it would be in slight disagreement with the initial offer. The offer would expect more, and the answer would only give this partial response. So there is some of that going on here. It could happen that there would be some need to intervene and edit the answer, but I'm not doing that. Okay, so I'm setting this answer as is, and then I am preparing a payload that will be carrying that answer to the signaling server, and then the signaling server will forward that to phone 1. So I'm setting all the attributes such that it gets delivered and correctly interpreted by phone 1. And then I'm sending it here. And prior to sending it, I am logging this. And that is where this comes from. Send answer to offer from phone 1. And then this answer gets delivered to phone 1. Let's have a look at what phone 1 does to this answer. So because this answer is carried through the signaling server, it's going to be handled here because this is where the messages are handled. So when the message is of type answer, there's going to be a special handler for that, handle answer. So what does it do? It grabs the message, and then it grabs the connection, peer connection, that corresponds to the sender of this message. So this gives us this reference here to that object. Then I'm logging it. I'm saying handling answer from, and then I'm specifying who I'm handling the answer from. And then I am doing this. I'm setting the remote description on phone 1 to be equal to the answer payload that PC sent to phone 1. So it's a sort of like a symmetrical situation where PC sets its remote description to the offer that was sent from phone 1, and phone 1 sets its remote description to be the answer that is sent from PC. Essentially, they both share each other's intentions and capabilities and exchange them, and then they remember in the peer connection objects what the peer is trying to do. So that's the idea here. So the peer connection object learns about its peer. And after this, it will be possible for phone 1 to receive ICE candidates from PC and then update this peer connection with those ICE candidates. Okay, what happens after this? So we saw how the offer was received here. So received signaling message, handling answer from PC. So we saw how that happened. This is also happening. ICE connection stage change. And this is very important. And I already mentioned what it represents. It means that the client is trying to test out the ICE candidate. And this also happens here. ICE connection state change for rather earlier, ICE connection state change. Well, let's have a look at what causes this. So I don't do any actions with it, but I'm logging it because it's very important to know where it happens. So this is going to be inside create a peer connection, where the peer connection object is created and all the listeners are set up. So it's happening here. So on ICE connection state change. So let's have a look. ICE connection state change. That's what I'm catching here. So I'm sending the centralized log message to the signaling server, also doing the local logging. So something notable that is happening here. So between handling the answer and then setting the remote description, which is coming from here. So handling the answer that is coming in from PC into phone 1, and then setting the remote description, which I am announcing here. Between these two events, I got a signaling message, and then I received a candidate as part of that signaling message. So what's interesting is these two happen in between these two. Another important observation here is this: on ice gathering state callback called. This log signifies that something changed about the ice gathering process. So initially, this was called on phone 1 when the connection was initiated early on in the process. So this meant that phone 1 wanted to start gathering ice candidates. So it gathered a whole bunch of them, sent them to PC, and then closer to the part where the connection was established, this callback, this handler was called again. But this time, this was announcing the end of the process, because right after this, phone 1 receives the final and completing ice candidate. And what I mean by this is this ice candidate marks the completion of the process. So this means the gathering has ended. No more ice candidates will be gathered. And the same thing is happening here on PC. So when it's starting to gather ice candidates, it starts here, and then it receives a whole bunch of ice candidates, and it sends them. And then after this, once it's done, it announces it here on ice gathering state callback called, and then it receives the final ice candidate. So that is a very important detail to note, that this handler is announcing the end of the ice gathering process. We got to the end. So what happens here? Peer connection established. What is going on here? This is very important, obviously, because this is the result that we want to accomplish. This is the result that means that data is finally being exchanged between the peers. So let's have a look. So we're looking at the peer connection handlers, and this is the one we care about on connection state chain. So I receive an event here, and then if the event connection state is equal to connected, that means success. I'm logging this extensively on the browser side, but on the signaling server side, I'm just logging it like this: peer connection established. And then after that, I am modifying certain things. So I'm resetting my Boolean here, which I use to determine the logic for whether I should reciprocate or not with the response. So my goal here is to determine whether this particular client should call back or not. So if this flag is false, and the two-way is toggled, to two-way switch is toggled on the UI, then I will call back. So I'll initiate a peer connection. I've already shown how this works. This creates the peer connection if it does not already exist, or if it already exists, it'll grab the existing one and then add the audio track to it. So that's what's happening here. Now, the way I determine whether outgoing audio is happening or not is using the browser API, WebRTC API that lives in the browser. So I check the statistics, stats in the peer connection. Then for each stat, I investigate whether there is an outgoing audio. If I find that, then I modify this to be true. And then that means when I get to here, this will be true. And therefore the opposite of it will be false. So this will not happen. If I never encounter this, it means there is no outgoing audio. That means it's okay to call back, assuming the two-way toggle is switched. So that's what's happening here. After this, there is another possibility, right? So either the connection state is connected, or it's disconnected or failed. Now, this goes back to that widget property that I was adding to the peer connections. So if the connection state has changed to disconnected, or changed to failed, what I'm going to do next is close the peer connection and then remove the widget. And it's going to be very simple. All I need to do is just make sure the peer connection has a widget. If it does, I'm going to go through the connection list and then remove the widget from that list, the list of widgets, and that's it. And then I'm also going to delete the peer connection after I closed it. I'm going to delete it from the map. And then I'm also going to release the wake lock if I have no more peer connections. That way the screen can go dark. What's nice about this approach is that the same peer with the same ID can come back and reestablish a peer connection, and that will not interfere with anything within the map, because the map will be cleared from that original ID. Another notable thing here is that when the connection is established, there is nothing I need to do in order to play the audio, because the peer connection already has the placeholder audio logic set up. So all it was waiting for is for the data to arrive, and that's it. It will start playing audio automatically. So before wrapping up the video, I'd like to mention two more things. One is about how I do the deployment. So the way I deploy is fairly standard for a vanilla JS application. So what I do is I have a grunt file that goes through the files, minifies them, and then puts them in a separate folder. And my Nginx will serve that folder. So how does minification look like in my case? So for app.js, it'll just obfuscate it. And then also it'll replace WS. So I have WS somewhere here. Here I have the reference to, I have this template essentially for the WebSocket URL, WebSocket address, and I'm replacing it with a secure one. So instead of WS, it'll be WSS. I have a similar thing in the debugger that produces the sequence diagram. So it grabs the logs from my signaling server, and same thing here. It will be obfuscated, and then also this will be replaced with WSS. So, and also the obfuscation happens with the CSS files for my debugger and the app.js, and the index.html, the one that opens the main application, will have its references updated. So by default, this is going to be the local version that is going to be used for local development. However, for the production, the references will be updated by replacing this with min.style.css, and then this will be replaced with min.app.js. And the signaling server stays the same in production. The only thing to note here is that my Nginx server will be acting as a proxy, so all the incoming signaling messages will go through the Nginx, and then it will forward the messages to this port. This WebSocket server is never exposed. It only communicates through my Nginx. And that's pretty much it with regards to the deployment. Another thought I have is about the actual development process. So obviously, as I was developing it, I had to use the microphone. I had to use web browsers on my mobile devices, on my other devices, and there was a problem. Web browsers do not like to give access to the microphone from insecure origins. Obviously, my local host was an insecure origin, and so I had to do something. Fortunately, there is a way to fix this problem. So if you go through, let's say what I have here is Chrome. So what you can do is you can go through those deep settings and then enable insecure origins treated as secure. You can enable this feature or this setting, and then it allows you to put the addresses or insecure origins here where the application will be opened. And this will allow the browser to treat it as a secure origin, and then the microphone will be enabled. So this is something to know going in when dealing with microphone related front-end applications. This is not really about WebRTC. This is about anything that runs in the browser that needs microphone access. So yeah, those are my final thoughts.